Hello everyone, welcome to today's webcast, which is about how human gait responds to muscle impairment in total knee arthroplasty patients. It's a simulation of muscle weakness in any body modeling system. So before we start the presentation, this is the outline of the webcast for today. So I will give you the introduction. My name is Mohammed Shurije. I am an R&D engineer at Anybody Technology. Following that, we're going to have a main presentation by Dr. Marzieh Ardestani from Rush University. She will talk about the motivations and goals of basically the webcast and her research. She will talk about the details of the model and then the details of the data analysis processing. And then I'll give you some words about the upcoming events of Anybody, and then we're going to wrap up with the questions and answers session. For some of you basically who haven't joined the webcast before, you're going to see the control panel on the right hand side. You can collapse or expand this control panel by pushing the red or orange button. If you think of a question during the presentation, please don't hold back and don't wait until the webcast is over. Just open the control panel and you can basically write your questions immediately. We will try to answer as many questions as possible at the end of the presentation. Some of our panelists as well may basically answer your questions directly. Or if your question is not answered, we'll try to do so by email in a few days. And also I should mention that the recording of the webcast basically will be available in a few days, and you will receive an email that includes the link to the recording. So any body modeling system, basically in Anybody you can simulate musculoskeletal simulations, which is based on multi-body kinematics and dynamics analysis. And besides that, you have the Anybody managed model repository, which is a repository that includes generic musculoskeletal models that are contributed by different researchers and developers all over the world. And there are specific basically simulation features that are beside the standard pipeline that you use for musculoskeletal modeling. So we have those special features in Anybody. For example, we have the reaction force prediction, which one example is ground reaction force prediction. Just think of a case that for gait analysis you don't have enough force plates to capture ground reaction forces for a gait cycle. So basically you let Anybody to estimate and predict those reaction forces for you. We also have a very efficient tool that you can basically have subject-specific information of the images of the bones, so you can do basically subject-specific morphing of the bones. And also we have the man-machine interaction simulation, which means that you can import easily and efficiently your CAD models into Anybody. Just imagine that you have a CAD model in SolidWorks. The parts will be automatically converted to rigid body segments, and the mates in SolidWorks will automatically be converted to rigid body joints. There are a bunch of applications of Anybody. Basically, the main standard one is basically the movement analysis. One example is gait. So you can basically have your motion capture data and ground reaction forces, and you can run Anybody to have access to internal loads, muscle forces, muscle activations. You can also do product design optimization. So if you have a conceptual CAD model or you have a prototype and you want to make it better, you want to run design optimization, and you want to see the interaction between your design and the human body, you can do it in Anybody. You can run ergonomic analysis. For example, this example, which shows the ingress-egress application. Basically, let's say another example can be where the steering wheel should be to maximize the comfort of the driver. You can also do basically the comparison between pre and post surgery. So basically anybody can help you to do prediction of the outcomes of the surgery. And also you can export any body information like variables of muscle forces, joint loads, etc. And those will form load cases for finite element analysis for you. So to run any body simulations, basically you need to have motions and external forces exerted to your body. Then you need the body model or the generic musculoskeletal models that you can get from any body model repository. And then, for example, you have environmental CAD model that all of these will come together to basically form the whole dynamic system for you. And then you can run inverse dynamics analysis to have access to basically variables of interest. So those variables can be muscle activity, muscle force, muscle metabolic energy. The variables can be ligament forces or joint loads that include the contribution of muscle forces. Or you want to look at the human environment interaction forces. So basically what are the forces at the straps for exoskeleton, what are the forces let's say for the reaction forces prediction that I already mentioned. And then you can use these output variables to do a post-processing in finite element tools, which, as I already mentioned, will be like load cases for you. Or you can close the loop to do design optimization. Basically, these human-related variables will give you feedback to your design, and you can basically use this feedback to make your design better. So now it's time for the main presentation. So I'd like to give an intro of our guest speaker, which is Marzieh Ardestani. Dr. Ardestani got her bachelor's and master's degree in Iran, and then she went to China at Zhangjiao Tong University, hopefully I pronounced the name correctly, to do her PhD in mechanical engineering. And then since 2015, she has been a postdoctoral fellow at the Rush University Medical Center in Chicago, United States. Her research interest is in biomechanics and orthopedic surgery, in particular motion and interacting surfaces. She started to apply the technical principles of kinematics and kinetics to natural systems in an effort to expand the body of traditional medical knowledge through engineering practices. In order to comprehend the effects of loading and movement at the joint, she uses motion analysis techniques and in silico simulations, including a number of computational approaches like multi-body dynamics and finite element analysis, combined with pattern recognition algorithms such as artificial neural network, wavelet analysis, principal component analysis, etc. Her current research has focused on gait features in patients with total knee arthroplasty, osteoarthritis, and anterior cruciate retaining. So without further hesitation, I would like to give the mic to Dr. Marzieh Ardestani. Hello, Marzieh, can you hear me?
Yeah, I can hear you now. I'm unmuted, right?
Okay, yes, perfect. So I think everybody can hear you now. Please go on with your presentation.
Yeah. Okay, hello everybody. Thank you so much for taking your time to joining us on this webinar. Thank you so much, Mohammed, for organizing this webinar. So my name is Marzieh, and I'm here today with you to share one of my recent projects using anybody and how anybody can actually be helpful for, how anybody could help us to calculate the muscle forces. As Mohammed explained, my current focus of research is computational biomechanics. So I'm trying to use musculoskeletal modeling in order to predict the outcome of rehabilitation or to predict the outcome of surgery. Today's talk is about how to use any body musculoskeletal system in order to simulate muscle impairment and then estimate how muscle impairment can affect humans' gait in total knee replacement patients. Okay, so total knee arthroplasty or total knee replacement, as you may know or heard about it, is to replace the natural human knee joint with an implant, or which is actually the ultimate treatment for severe knee osteoarthritis. The main goal of this surgery is first, pain relief, because as we know that patients at the end stage of knee osteoarthritis usually experience a very severe pain, which actually prevents them to participate in daily life activities. The second goal of total knee arthroplasty is restoration of normal alignment of the limb, and the most important goal is to restore the knee function, either in terms of mobility and stability. And these two are translated in terms of gait. The knee function, either in terms of mobility or stability, show itself in terms of gait pattern. Okay, but what will happen after total knee arthroplasty? So we have replaced the diseased joint with a very developed, fancy implant, and we expect the patients to recover from the surgery, stand on his feet, and then start walking. But what will really happen to the human gait after surgery? Well, unfortunately, there are a bunch of barriers which prevent the patient to restore normal gait following surgery. For example, those pre-surgical gait adaptation that a patient has chosen before surgery, they usually persist a long time after surgery, or the joint range of motion is usually decreased following surgery. The fear of fall, and most importantly, the muscle weakness. Muscle weakness is the main factor which prevents patients to restore gait following total knee arthroplasty. There are some literature available which compare the muscle strengths before and after surgery. For example, from the literature, we can say the quadriceps strength will be reduced to 50 to 60% after surgery. The quadriceps and the hamstring, as the main knee flexor and extensor muscles, their strengths will dramatically reduce after surgery. This is the bar graph to compare the pre-operation strengths in surgical and non-surgical knee, and then 1 month post-operation, and then 6 months post-operation. As you see, even after 6 months post-operation, the quadriceps strength is still asymmetry between surgical limb and non-surgical limb, and the surgical limb shows a decreased amount of strength compared to non-surgical. And this is the strength comparison for hamstring, again in pre-operation, 1 month post-operation, and 6 months post-operation. So muscle weakness happens after total knee arthroplasty, and it can persist up to 3 years after surgery. And we know that the muscles play a very important role in forming and shaping the human gait pattern. How you walk, how you flex different joints, it's directly dictated by the muscle strength. So our main question is that, well, now we know that muscle weakness happens, but how the human modify his gait in case of muscle weakness? How much weakness can be tolerated by our gait? Well, a subtle weakness in an individual muscle can be compensated by additional contribution of other muscles. And I'm sure that all of us have experienced this case in our daily life. So after a heavy exercise, in gym or after exercise, a football exercise, we usually experience muscle sore in our thigh or in knee flexor muscles. What usually we do the day after that? Well, it's a little bit limping in our contralateral limb, and then we handle our daily life. We try to compensate the pain or whatever impairment that has happened in our individual muscles by the help or compensations of other muscles. But, well, severe muscle impairments, like those that happen post-operative in total knee arthroplasty patients, cannot be easily compensated, and it will lead to kinematic compensation or kinematic adaptations in human gait, like quadriceps avoidance or knee stiffening strategies are two popular examples of kinematic abnormality which is observed after total knee arthroplasty. Our main research question is therefore how much muscle weakness can be tolerated by total knee arthroplasty patients before demanding any kinematic adaptation, and then how muscle impairments may perturb muscle and joint forces. This is the original paper that has been published in Journal of Biomechanics. And I'm going to review some of the modeling details that we have used Anybody modeling system for this publication. And I'm going to review the method and mostly some model details and what we have done in this paper. Okay, so first of all, we are interested to know that how total knee arthroplasty patients walk in terms of well, full strength muscles. If their muscles have full strength and are not impaired, how do they walk? And then how do they react to any muscle strength reduction? So the muscle strength reduction can be performed in two ways. Stepwise reduction, that we reduce the muscle strength in the step of 1% or 2% until the model is getting completely unpaired and cannot walk at all. And the second part is that we randomly perturb the muscle strength in order to create a probabilistic space of all possible conditions for muscle weakness, and then we simulate how human joint loads and muscle forces will react to this reduced strength. We have done two post-processing stages in order to compare the simulation, joint and muscle forces from full strength simulation to reduced strength simulation. We use a spatial parameter mapping and principal component analysis as two post-processing stages. I'm not going to review the details of these two techniques, but all the details are available in the publication. So I could ask you that if you are interested to investigate more about post-processing, you can actually refer to our paper. But let's start with reviewing the multi-body dynamic and then how muscles are modeled in any body. Okay, so just for a very quick review, we know that the hip extensors and hip flexors, knee flexors and knee extensors are the main groups that actually direct the human gait. Here I have a quick review of the knee flexors and knee extensors, the vastus medialis, rectus, and vastus lateralis, which actually grouped as the quadriceps, and then biceps femoris and semitendinosus and semimembranous that are considered as hamstring. We also discussed the ankle plantar flexor and ankle dorsiflexor muscles, including the tibialis anterior, and then pronus, gastrocnemius, soleus, and adductor magnus, and sartorius. All of these muscles have been modeled in any body modeling system. And here is the musculoskeletal model that we have used. It has been borrowed from Klein Torsman PhD dissertation. This model is published. I think it's available in the Anybody repository. So the hip joint is modeled with 3 degrees of freedom, a ball and socket. The knee joint is a hinge joint with 1 degree of freedom for flexion extension, and the ankle joint has been modeled with 2 degrees of freedom for ankle flexion extension and subtalar inversion. The muscle model is the heel type muscle, and we have considered like 6 main muscle groups as hip flexor, hip extensor, hip abductor, adductor, ankle plantar flexor, and ankle dorsiflexor muscles. And we go through each muscle group. We simulate weakness by reducing the strength in each muscle groups, and then we run the multi-body dynamic analysis to calculate joint forces and muscle forces and see how the human gait is handling muscle weakness. So this is a very quick and brief review over the process in any body modeling system. The first step is scaling. There are a number of different law and procedures for scaling a musculoskeletal model in any body, but perhaps the more completed or the best one is length mass fat, which actually scale your generic musculoskeletal model based on the length, considering the mass and weight of the subject, and also considering a coefficient for body fat. After scaling the model, we run the motion and parameter optimization, and then finally the inverse dynamic analysis. So in motion and parameter optimization routine, we calculate the joint kinematics from marker trajectories, and then in inverse dynamic analysis, we use those joint angles in order to calculate the joint forces and muscle forces. Okay, and how the muscle has been modeled in any body modeling system? Well, as I said, the muscle model the muscles are modeled as a heel type muscle model, but how it works? Well, each muscle model in any body consists of 2 parts, the kinematic model and then the strength model. And the parameters of this kinematic model and the strength models are adjusted during the scaling session when you scale your musculoskeletal model. The kinematic part calculates the length and the contraction velocity of the muscle as a function of body posture and muscle path. And after that, the strength model comes to play. It determines the muscle strength as a function of kinematic state of the muscle. Here is the equation which describes a muscle model in any body modeling system. So the muscle strength is a function of muscle isometric strength, the contraction velocity, the current length of the muscle, and the contraction velocity at maximum voluntary contraction. This is how a muscle strength is defined in any body modeling system. So if we choose to reduce the muscle isometric strength, F0 in this equation, we can stimulate muscle weakness. If you decide to simulate other kind of muscle impairment, for example, delay in the activation, or say, for example, a weakness in muscle activation, you can definitely play with other parameters in this equation. You can choose to reduce or increase any like neutral fiber lengths or the contraction velocity and see how your gait will respond to any source of muscle impairment. But for this study, we have decided to choose muscle weakness, simulate muscle weakness. So we are reducing the strength through a reduction in muscle isometric strength parameter, or F0 in this equation. And then how muscles are hired in any body modeling system. So we know that as a general rule, the human musculoskeletal model or our body is the musculoskeletal is a redundant system, which means that it has more number of muscles than the degree of freedoms. So each degree of freedom in our joint can be controlled via a lot of combination of different muscles. But how the central nervous system is going to control our movement, or how it uses muscles to control each degree of freedom, well, it is described through an optimization routine, which means that the muscles are hired somehow in order to minimize the maximum of muscle forces. So the muscle forces are computed through an optimization routine. We define an objective function, which is a function of muscle forces and joint reaction forces. And then we try to minimize this objective function, calculating the muscle forces in order to minimize this objective function. Again, these two are the equations that actually the muscle recruitment procedure in any body has been defined based on. Okay, so we run 3 types of multi-body dynamic analysis in our study. The first one is the inverse dynamic routine. We import the marker trajectories and the ground reaction forces collected from patients with total knee replacement, and we go through scaling the musculoskeletal model through the optimization routine to calculate the joint kinematics, and then finally through the inverse dynamic routine in order to calculate joint loading and muscle forces. The second run of multi-body dynamic analysis, we start to reducing the isometric muscle parameter, muscle force parameter, in order to simulate muscle weakness. For each group of muscles, like hip abductors or hip adductors or knee flexors, or every individual group of muscles, we start to reducing the muscle strength until the model fails to walk. And from this set of simulation, we can achieve the minimum strength requirements of each muscle group in order to execute gait. And then finally, the third set of multi-body dynamic analysis, we randomly perturb the muscle strength between its nominal value and the minimum strength in order to create a very large and probabilistic data space of muscle impairment. And then we again run the impaired musculoskeletal model in order to calculate joint loading and muscle forces. And then we compare the gait in terms of kinematic to see whether the gait is normal or not. We actually compare the first set of results. The first set of joint forces and muscle forces come from the first multi-body dynamic, a nominal strength model, with the third simulation, that we have simulated the muscle weakness to see if the gait kinematics have been changed or not, and how the muscle forces actually have reacted to this weakness. And in order to compare the first set of simulation, the nominal simulation, with the third set of simulation, we use a spatial parameter mapping, which is a statistical test in order to compare gait waveform through the whole gait cycle. And then we also do a principal component analysis in order to measure the sensitivity of each joint force or joint muscle due to perturbation in the individual muscle strength. And I said, we don't have enough time to review the details of these two techniques, but details are included in the paper, and you can actually study the paper for further details. Here are the results. So, from stepwise reduction of muscle strength and then running the musculoskeletal model with the reduced strength muscle models, we can estimate how much strength is needed for each muscle group in order to execute gait. Well, we realize that the hip extensor needs at least 65% of the baseline in order to execute gait. Hip abductor, on the other hand, or hip adductor, on the other hand, they need about 46% of the baseline strength in order to execute gait. What does it mean? It means that if we get a reduction in muscle strength for more than 50% in, for example, knee extensor or hip adductor or hip abductor, then the person won't be able to complete the gait task. So we can have an estimation of, the role and the importance of each muscle group in shaping the natural gait. Now we want to look closer what will happen in other muscle forces when the hip extensors are weakened. I will review just a couple of individual muscles. The Anybody Musculoskeletal model, the model that we have used and it's available in Anybody repository, has more than 100 muscle. We have studied most of them, but I'm not going to review all of them here, just to give you an example that, well, if hip extensor is weakened, then how gastrocnemius is responding to this weakness. So this is a comparison of gastrocnemius force over the whole gait cycle. We have normalized the gait cycle to 100 sample, and it shows that, well, the black line is related to natural gait without any muscle impairment, and the red curve demonstrates the mean and standard deviation of gastrocnemius force in terms of hip extensor weakness. As we see, the gastrocnemius increase its output force in order to somehow compensate the hip extensor weakness. The vastus, as another important muscle, how it reacts to hip extensor weakness. Well, when the hip extensor weakness is simulated, we see that the vastus increase its output force, especially during the swing and especially during the mid stance. How about for hip flexor? If we simulate any weakness in hip flexor group, then the vastus, again, it reacts, but it reacts differently. So the force, the vastus force, will increase in terminal stance. And how the quadratus react? Well, again, the quadratus is one of those muscles which increase the muscle forces in order to compensate for hip flexor weakness. We have repeated this procedure over almost all the muscles and muscles included in the model. So we simulate the weakness in a group of muscles by reducing its maximum isometric force parameter and then we run the inverse dynamic. We calculate the muscle forces and joint loadings and see how other joints and muscles have been reacted to this change in musculoskeletal system. Here is an example of how the hip forces, anterior, posterior, or medial lateral force components have been reacted to hip flexor weakness. So for example, here we see that hip anterior, posterior have been remarkably increased in terminal stance, but on the other hand, hip medial lateral have been reduced in mid stance in terms of hip flexor weakness. We have calculated the sensitivity of every joint force component to the weakness of individual muscles. So how sensitive is the hip force to weakness of every individual muscles to gluteus maximus? How hip force is changed if the gluteus medius is weakened, or how about if we have a reduction in a strength factor of biceps femoris or rectus femoris? We see that how anybody can help us to calculate the joint forces in response to individual weakness in muscles. We can quantify the sensitivity of joint forces to individual muscle forces. We know that in experiment, it usually costs a lot of time and money to recruit patients. And then how you want to study or separate the influence of individual muscle weakness. It is almost impossible, but using the computational techniques like multi-body dynamic, now we are able to separately weaken one muscle, individually impair one muscle, and see how other joint and muscles are reacting. We can quantify the human gait response. Okay, so in the model that we have used, and again, this model is available in any body repository system, we have feed our model with marker trajectory and ground reaction forces collected from total knee replacement patients. We haven't replaced the knee geometry with the knee implant geometry for this study, but we have another study with any-body musculoskeletal model, prediction of in vivo joint mechanics of artificial knee implant using rigid multi-body dynamic with elastic contacts, that one of my colleagues have conducted this, and we have replaced the geometry of a natural knee with the geometry of knee implant. As Mohammed explained at the start of the webinar, anybody has this ability that you can scan like a knee implant or a hip implant, and then you can have the CAD or three-dimensional geometry of your model, and then you can replace this model in the generic musculoskeletal model, so you can replace each joint with a specific implant. We have done it in the past. The problem is that, and here is how the model looks like. So you can replace the knee joint with the geometry of an implant, and then you can calculate all of the contralateral ligaments. But the problem with this model is that it takes a little bit long to calculate the muscle forces and joint forces over the entire gait cycle. Well, it is not very surprising. We are importing more complicated geometry to the model, so it will take a little bit longer for the model. For the purpose of our study, to study how human gait responds to muscle weakness, we need to run thousands of inverse dynamic simulation, and simulating like thousands combination of muscle impairment or muscle weakness together. So we just try to use a model which calculate the forces faster, but also this model is available if you are interested to replace the natural knee geometry with the implant geometry. Yeah, have a very quick overview. Well, the probabilistic multi-body dynamic analysis was used to evaluate the minimum strength requirement of muscles, quantify the minimum strength requirement, and then quantify how muscular system is responding to muscle weakness. And we have used any body modeling system to simulate the muscle weakness. As I explained, the mathematical equation of muscle strength in any body will enable us to play with different parameters and simulate different types of muscle impairment. Thank you, everybody. Thank you for listening. And yeah, I'm here if you have any question.
Okay. Thanks very much for the interesting presentation. I think you did a great job of explaining basically the details of the workflow, how we can use the data to basically run the antibody model and to get results, and basically very interesting results about muscle weakness and how it fits basically different applications. So I think you showed the results for TKR, but you know, this approach can be used for other approaches as well, and for other like populations like osteoarthritis, for example. Okay, so before going to the Q&A session, I would like to show you some slides. Okay. Yeah. So it's about our future webcasts. So there won't be any webcast basically during summer 2016, and the new round will start probably late August or September. I encourage you to check out our YouTube channel for previous webcasts, for example, the ground reaction forces. Lots of people like to know more about ground reaction forces. So if you go to our YouTube channel, you're going to see the list of all previous webcasts. Please visit our website, and you're going to see a lot of useful links. You're going to see the future events, publication lists related to your own or specific research of interest. And you can visit anyscript.org. So Anyscript is the programming language of anybody, and there are wiki pages and forums that you can post your questions, or you can find interesting and useful information about any scripting. So upcoming events that anybody basically will participate in. So we're going to be in European Society of Biomechanics in July, and we have a hands-on training workshop there, so it's free of charge, and the seating is basically limited. So if you want to reserve a seat, please do so as soon as possible. So we're going to be there for the whole conference. We're going to have a booth there as well. So if you couldn't make it for the workshop, please stop by our booth and you can have chat with our colleagues about your research, about use of antibody modeling system. If you're already a user, you can discuss your applications. We're going to be at the ASB, American Society of Biomechanics in Raleigh, the United States as well, in August. And you can see my colleagues there as well. And we're going to participate in the Wearable Robotics Europe Conference in Spain in October, and we'll present basically, we're going to have oral presentations as well as poster presentations about our exoskeleton applications. So make sure you visit us there. Okay, with this, I'd like to basically conclude and then go to the Q&A session. So I'm going to unmute you, Marzia. Okay, are you there?
Yeah, I'm here.
Okay,
thank you
perfect.
so much. Yeah. Well,
Yeah.
Okay, now I have received a bunch of questions from the attendees.
Okay.
Yeah.
Okay, perfect. Yeah. So let me read the questions so that other people you know, have a chance to hear them as well. So I have received several questions. I'm trying to organize them a little bit. Okay, I'll start with this one. Have you looked at the other direction in terms of which muscles patients would need to train to return the same gait of healthy controls?
Yes, actually the long term of this study is to somehow put different priority on different group of muscles for rehabilitation. So as we saw in our simulation, it seems that the hip flexor muscles could only be weakened by 65% of its nominal strength, which means that it can only tolerate 35% of reduction in the strength. It means that, well, if you are going to make a remarkable improvement in human gait, it's better to now focus on the hip flexor muscles. Yes, the long term of this study is actually to guide the rehabilitation process, that, well, which muscles we should choose to rehabilitate. And the answer to this question is that, well, those muscles that make that any impairment in them make a very large or remarkable perturbation in terms of other joint forces or other muscle forces.
I see. There's another question. Are these results in muscle strength based on an individual MVC, or are they based on an expected or standard MVC for a specific patient?
No, these are based on individual maximum voluntary contraction. So let me explain that the database that we have used for this study is the grand challenge competition data that have been published like a few years ago, and it is still available. So they have reported like not only market trajectory and the ground reaction force, but they have also reported the maximum voluntary contraction of hip extensor, hip flexors, and knee flexors and knee extensors. So you can actually use those values in order to make your generic musculoskeletal model as close as possible to a real total knee replacement patient.
I see. Here's another one. What are your validation procedures for the simulated weaknesses? Do you compare with patient EMG data?
Oh yes, again, one of the strengths of the database is that we have access to the experimental EMG, and then when we run the musculoskeletal model before simulating any muscle weakness, we have compared the muscle forces from our model with those which had been actually experimentally measured in the lab. So once we validated the simulation, then we feel more comfortable to like change different parameters of the muscle models and simulate muscle impairments. Again, for artificially impaired musculoskeletal model, also the general shape or the general waveform of muscle forces is still consistent with the experimental EMG.
Okay. Here is another question. So thank you for the nice explanation of your work. I wondered whether you checked how sensitive your results are to changes in the cost function you use to estimate muscle forces.
Oh yeah,
for example, it has been.
Yeah. This is actually one of the reviewer comments that we received once we submitted this paper, the Journal of Biomechanics, that definitely the parameters of the cost function also going to affect their results. Well, this wasn't the focus of our study, but definitely it could be the subject for another study, that any changes in central nervous system or any changes in motor control abilities, how it's going to affect human gait. And then to answer this question, you should manipulate the parameters of your optimization model. But this wasn't the focus of our study, but I fully agree that this is lacking from this paper, and this could be the subject for another paper or another study.
I see. That makes sense. And one question basically from us, which might be tricky to answer. Do you have a rationale for basically why the importance of muscle strength in sustaining gait decreases from hip to ankle? So those basically numbers that you said, you showed us about the percentage of reducing muscle strength. So it was greater
Yes.
for the hip, and it was basically decreasing as you moved on to the ankle.
Decreasing, yeah, okay. So those, yeah, it decreased from the hip to the ankle. Well, let's think about that. Well, the knee flexors and knee extensors are the main group of muscles which are controlling the knee movement, right? But these knee extensors and knee flexors also play an agonist-antagonist role for hip flexion and hip extension, such that your knee flexors participate in hip extensor, in extending the hip as well, and then your knee extensors participate in flexing your hip. So these muscles, especially those muscles that cross both hip and knee, play a greater role. When you impair your knee flexor, it is not only knee flexors that you are impairing, you are also impairing hip extensor at the same time. So yeah, this is the reason that I think the sensitivity is reduced from hip to ankle. And also, I think considering the knee adduction moment and knee joint forces, or because knee is tolerating several times of body weight during the stance or imposes on the knee, well, I think it's reasonable that gait is more susceptible to impairment in knee muscle weaknesses or hip muscle weaknesses than to ankle.
Okay, that makes sense. So thanks very much. So I'd like to close the webcast. I'd like to thank everyone for attending this webcast. Again, if your questions were not answered, first of all, we're very sorry, and we'll try to follow up. We will basically follow up with you via email in a few days. And again, so you'll receive an email with a link of the recorded webcast. So for some of you that missed part of it or were not able to make it to the end, thanks very much again. Thanks, Marzi, again, for the very nice presentation.
Sure. My pleasure. Thank you so much for giving me this opportunity to attend your webinar.
Okay, thanks very much, and everyone have a great time.
Have a good day. Bye.